All right, let's dive right in. Today, we're getting right under the hood of artificial intelligence to tackle a really fundamental question, one that gets to the very heart of how these incredible tools actually work.
So, how does an AI really think? I mean, when you type in a prompt and poof, a response appears, what is actually going on in there?
For a lot of us, the picture that comes to mind is this giant, endless library, or maybe a massive, hyper-organized filing cabinet, right? We imagine the AI rummaging through endless drawers of facts and sentences to find the perfect one. But here's the thing. That picture is just, well, completely wrong. In fact, the source material for this explainer puts it perfectly. The deepest mistake people make is to imagine that the model contains answers in some direct sentence-like way. So if it's not a library full of answers, then what in the world is it? The reality is so much more dynamic, more, well, alive. So let's just go ahead and shatter that filing cabinet metaphor right now. It's not about pulling a pre-written file from a drawer. It's more about generating a living signal that flows through this complex, pre-carved landscape. Okay, so to get our heads around this huge, complex landscape, we've got to start small. I mean, really small. Let's zoom all the way into the most basic building block of the whole system, the individual neuron. So, the first thing to do is to stop thinking of a neuron as some kind of tiny calculator. A much better way to think of it is as a specialized feature detector. That's its whole job. It has one mission: to watch for one very specific pattern in all the noise coming in. And when it sees that pattern, bam, it activates. And the process is actually pretty straightforward. A signal arrives. The neuron looks at it and compares it to its own internal learned pattern. We call these its weights. And if the patterns line up, if it's a really strong match, the neuron just lights up, it fires. If not, it just stays quiet, waiting for its moment. It's almost like you can imagine every single one of these billions of neurons constantly asking itself one simple question as the data flows by. Hey, does this new signal look anything like the pattern I'm tuned to detect? If the answer is a big yes, it fires and passes that signal down the line. Okay, so that's one neuron. But here's the wild part. A real model has billions of them. And when you get all of them working together, they create something we call the weight landscape. So all those individual patterns from all those neurons, when you put them all together, they form this vast, incredibly complex, high-dimensional landscape. Now, the training process, that's what carves out all the mountains and valleys in this landscape. And then when we ask the AI a question, what we call inference, we're basically sending a signal to flow through that pre-carved world. And there's a really powerful way to visualize this. I want you to imagine a super elaborate irrigation system. All the pipes, the gates, the slopes, the valves, they're all already built and fixed in place. That is the weight structure of the model. So let's just map this out clearly because it's a great analogy. The infrastructure itself, all the pipes and gates, that's the model's weights. They don't change. The signal, which comes from your prompt, that's like colored water flowing through the system. We call those the activations. And that whole event, the water flowing from the start all the way to the end, that's inference. That's the AI, right there, in the act of thinking. But it gets even cooler. Modern networks, like the transformers you hear about all the time, they take this whole circuit idea and just crank it up to 11. These aren't just rigid pipes, they're actually programmable on the fly. And this programmability comes from a genius mechanism called attention. So for every little piece of data, every token, the model creates three things. First, a query, which is basically asking, hey, who out there has information that's relevant to me? Then you have a key, which is like an advertisement, shouting, I've got information about this topic. And finally, there's a value, which holds the actual, juicy information that gets passed along if a query and a key make a match. So what happens is, based on your specific prompt, the queries and keys all start matching up, creating this brand new temporary wiring diagram just for your question. It's like opening and closing specific valves in that irrigation system in real time to create a custom path for the water. That's what this quote means. Attention is temporary routing over permanent circuitry. So good. Okay, so once attention has routed the signal to all the right places, it flows into the next stage, the MLP layers. You can think of these as the processing plants or the factories of the network. They take that signal, which is now full of context from the attention step, and they actually transform it. They refine it, they elaborate on it, they pull out higher level meaning.
All right, let's put all these pieces together. It's time to throw out that filing cabinet model for good and replace it with a new, way more accurate one: compressed semantic circuitry. I know it sounds like a mouthful, but let's break down exactly what each of those words mean.
First up, circuitry. The weights in the model aren't just a boring list of numbers. No way. They are an active system. They form all these conditional pathways that guide the signal, that amplify it, that suppress it, and ultimately transform it as it flows through. It's behaving exactly like a complex electronic circuit.
Next, semantic. This is the crucial part. This isn't a circuit for electricity, like in your phone. It's a circuit for meaning. The signals, those activations we talked about, they actually correspond to abstract concepts, to relationships, to the structure of language and ideas. It's a machine literally built to process semantics.
And finally, compressed. Look, the model was trained on trillions of examples. It can't possibly store all of that raw data. It would be impossible. Instead, it does something much smarter. It distills all of that vast experience down into a compressed, finite set of these pathways and rules. It doesn't store facts. It stores the reusable principles of how things relate to each other. So let's put them side by side and see just how different these two ideas are. The old filing cabinet idea, it gives you retrieval. It's all about finding something that's already there. It's passive storage. But the circuit, it gives you transformation. It's dynamic computation. It doesn't store facts as entries. It stores learned response tendencies. It's a fundamentally different and, frankly, much more powerful idea. So thinking this way, with this new circuit model, it completely reframes how we should think about these systems. It's not about what's stored inside. It's about the process of the signal flowing through. And this leads us to a final, really crucial distinction. I want you to think of it this way. The weights, those fixed pipes in our irrigation system, that is frozen learning. All the hard work from training is locked in there. But the activations, that colored water, that signal flowing through them right now in response to your prompt, that is living thought. And that brings us to what might be the single most important takeaway from all of this. An AI, an artificial neural network, does not mainly store answers. It stores ways for signals to become answers. The knowledge isn't a static thing sitting in a database. It's a dynamic event that emerges from the flow.